we will study is a STA problem. Last time we went across STA equations, basics of STA, basics of setup time and hold time. So now consider this problem. Okay, so in this following circuit what we have to do is like check whether there is a setup or hold violation, okay, for the given set of values, and T clock here it's given as 15 nanoseconds in advance. Okay, so now what we know is basics of setup equation and hold equation. Okay, so let's consider this. Okay, so T clock must be greater than T clock to Q plus TPD plus T setup. This basic thing we know. Now using our common sense, how can we solve this problem? Okay, so only one thing is required, is common sense. So there is term called as clock skew. Okay, so whenever you will do the analysis, we will so you need to check on the flip-flop 2 if there is a setup violation or not. Okay, so you need to check that. So which clock you will consider? You will consider this one, which is going to flip-flop 2, not this one, not this one. Okay, so now if you will see this circuit, this has some delays in it. Okay, there are some delays. So if you will see that our clock is already delayed by some delay elements, right? Now if you will see the equation, T clock plus some skew will be there because it's like delayed, should be greater than T clock to Q plus TPD plus T setup. Okay, now this will be the new equation, because see what you are doing is just delaying this from some X element, so some X delay is there. So T clock will be delayed by some X, so say X. Now if you will see this equation, what is the worst case scenario? If it works well in worst case scenario, it will work in the best case scenario as well. So it will be opposite to this equality sign. Okay, so we need to take this as minimum and take this as maximum. In this case itself we will get the worst case scenario. Now so what we got to know is data path delay must be maximum and clock path delay must be minimum. Okay, this will give us worst case scenario. Now let's calculate the data path delay, maximum maximum data path delay. So it will be T max, this is the first wire delay, that is 2 nanoseconds data path max. Okay, plus T clock to Q max 11 nanoseconds plus T max 2 nanoseconds plus this inverter delay is 9 nanoseconds plus again the wire delay 2 nanoseconds. This gives us 26 nanoseconds. Okay, data path delay is 26 nanoseconds. Now clock path delay is T minimum 2 nanoseconds, buffer delay 5 nanoseconds plus 2 nanoseconds. This gives us 9 nanoseconds. Now let us give this value. T clock is 15 nanoseconds as given in this example, plus 9 nanoseconds must be greater than 26 nanoseconds plus T setup, that is 4 nanoseconds. This is 5 plus 9, 24 nanoseconds greater than 30 nanoseconds, which is completely wrong. So the setup time is violated here. Setup violation, not setup time, setup violation is there. Now if we want to calculate on which frequency this circuit will work. So what we can do is we can give this as t clock as a variable plus data path minimum delay. What is the data path minimum delay? 9 nanoseconds plus the clock sorry, this is clock path delay. Okay, now data path maximum delay is 26 nanoseconds and plus t setup, that is 4 nanoseconds. So t clock must be greater than 21 nanoseconds, then only this circuit would work fine. Okay, got it? Now graphically also I can show you this. This is flip-flop 1. So the time period is 15 nanoseconds. This is for flip-flop 1, this clock. Now this is flip-flop 2. This one is flip-flop 2. This from there to here, it's 9 nanosecond delay already. Okay, from first edge to first edge, second edge to second edge. Okay, got it? Yeah. Now what we need to do is, so now data, that's data is how much? 26 nanosecond delay, and plus setup time is 4 nanoseconds. So this must be like stable for, like when this is here, so this must be like coming before this. But see, 9 plus 15 is 24 and this is 30. Okay, so this signal will be stable after this point, so setup time is violated. Okay, got it? Now t hold time, t hold must be less than t clock to q plus t pt. So this delay should be more than this delay, and plus the clock skew. But this case, what will be the worst case? According to this must be minimum and this must be maximum, so clock skew must be maximum. So now we need to calculate clock data path max, that is 3 nanoseconds plus 9 nanoseconds plus 3 nanoseconds again, that is 15 nanoseconds, and hold time is 2, so plus 2 nanoseconds. So left hand side is 17 nanoseconds. Okay, now we are considering each thing. So hold time is calculated for the same clock edge, but setup time is calculated for one clock is after. Okay, so that's why we are incorporating this error, because maximum delay from flip-flop 1 clock to flip-flop 2 clock is 15 nanoseconds. This will be 15 nanoseconds, right? And then it will come, right? So this we need to do. Got it? Now if you will see data path minimum delay, you will see 1 plus 9 plus 1 plus 6 plus 1, that is 15, 17, 18 nanoseconds. Now 18 nanoseconds is always greater than 15 nanoseconds, right? 15 plus 2, 17 nanoseconds, right? So the 1 nanosecond positive. So this is not violating hold violation. So it's like hold violation is not there in this circuit. So this is how you can do these things, and if you like